So, Professor N. Haridas, QCD string and effective string theory. Please start, sir. Please.
Thank you. Where are my slides?
Okay, just give us a second. Sorry.
I don't see my slides.
Yeah, just give us a second, please. Yeah.
Yeah.
Just a second.
Anyway, in the meantime, it's a great honor and privilege to be part of this meeting to remember our dear teacher, Professor Mitra. I was a student both in my honors and in MSc days, and afterwards we were constantly in touch with each other. And as I will explain in my talk, he is the one who opened my eyes to the world of elementary particles, and in particular, the quark model. So is this full screen? It doesn't seem to be. Alok?
It is not a full screen, but still we can see.
Let me try. Sorry.
Okay, so I'm going to be talking about the topic QCD strings and effective string theories. This summarizes a body of work, both analytical and numerical, that I have done with several of my collaborators. And this will be a summary. And in a way, it's a very apt tribute to Professor Mitra, as he is the one who introduced me to the quark model. So my academic journey began with the quark model, and more or less, the end point of my academic journey, formally speaking, also had to do with quark theories. Next slide, please. So, tribute to Professor Mitra. He really opened our eyes to the magical world of elementary particles. To say that is only an understatement, but by the end of this symposium, we will all know the true import of his impact on all of us. Next slide, please. So this is the stage where it all happened. The wonderful days of our honors and MSc in Delhi University, all the lectures were here. Professor Mitra's magical lectures on mathematical physics also started our interaction at what I would call this the unforgettable stage for me. Next slide, please. So, quarks, Mitra, and me. The quark model was proposed independently by Gell-Mann and Zweig in 1964. For my MSc thesis in 66, 2 years after the quark model was founded, Mitra suggested working on the meson and baryon decays in the quark model. He was clearly among the few worldwide that took the quark model seriously right from its inception. As we all know, not everybody took this model very seriously. The year after that, in 67, I went to UC Santa Barbara, barely 100 kilometers from Caltech, where the quark model was born. And incidentally, while writing my recent book, I discovered a Mitra-Santa Barbara connection, which was the paper by Mitra, Gillespie, Bob Sugar, and Nargis in 65 on 4-particle scattering. But nobody took the quark model seriously in Santa Barbara, for that matter, in the whole of the West Coast. Feynman even made fun of them, calling it the quack model. So that was the situation. Next slide, please. Now let me go a little bit deeper into the quark model. The quark model was an outgrowth from the so-called Sakata model, eightfold way, SU3, etc. Incidentally, the spectacular prediction of the omega minus owes it to the eightfold way and not to the quark model, as is often or sometimes claimed erroneously. The Sakata model needed anti-baryons even to build baryons, and to avoid this, Gell-Mann and Zweig introduced fractional baryon number and fractional electric charge for the quarks. Almost immediately, the quark model was seen to suffer from the so-called statistics problem. In 65, a year later, Hahn and Nambu came up with an alternate quark model, which not only proposed ways of solving the statistics problem, they did not call it color, but also paved the way for quark dynamics through what is now known as the gauging. Next slide, please. In hindsight, it was a monumental opportunity missed that we did not study the Hahn-Nambu paper more closely and focus more on the Gell-Mann-Zweig model. And this regret is not just mine. No less than Gell-Mann himself had this to say. He said, if I had read Nambu's paper, it would have set me ahead by several years. And in another context, he said, Nambu then invented what amounted to QCD, or the beginning of QCD. Next slide, please. So now I'll briefly talk about the birth of what we call the quantum chromodynamics. The attractive feature of the Hahn-Nambu model was the electric charges were integral, unlike the fractional charges of the Gell-Mann-Zweig quarks. But a heavy price to pay for this was that there was an unavoidable mixing of flavor with color. It took almost a decade for the correct identification of color in the Gell-Mann-Zweig quark model. But when they did identify, it was a supremely elegant solution and completely avoided any color flavor mixing, leading to quark dynamic, color dynamics, which is completely flavor blind. And that has played a major role in the development of QCD. It was identified by Gell-Mann and Fritsch as the fundamental representation of a new SU3 group called the color group. Quark dynamics was realized through the Yang-Mills theory of the color group. Rather ironically, even to this day, there are no acid tests to distinguish between the integral charge Hahn-Nambu model and fractional charge Gell-Mann-Zweig theories. This was shown by extensive works of G. Rajasekhar and his collaborators. Next slide, please. Not everyone subscribed to the quark model for a variety of reasons. Even quantum field theory itself was discredited on the West Coast, where I went to do my PhD. And, instead, it was the S-matrix approach pioneered by Heisenberg that was very strongly championed. After a decade-long, rather impressive line of developments like dispersion theory, dual resonance models, the relativistic strings idea was proposed in 1970 by my dear friend Holger Nielsen, Nambu, and Susskind to explain many features of strongly interacting particles called hadrons that could not at that point be explained by any relativistic quantum field theory. But this idea also ran into several difficulties, as it required space-time dimensions to be 26, tachyons, etc., and was abandoned by many in favor of the Gell-Mann-Fritsch quantum chromodynamics. The punchline of our work is the emergence of strings within QCD itself. So in a rather remarkable way, these two divergent paths are now brought together. Next slide. The major unsolved problem for QCD is that of quark confinement. Simply stated, no free quarks had been observed even during very energetic collisions between hadrons. That would not be so if hadrons were bound states in the traditional sense of a quantum field theory. What should have been a theoretical embarrassment was turned into a virtue with the proposal that quarks are permanently confined. And this is the principle of permanent quark confinement. But the challenge was, it was far from clear if any quantum field theory, leave alone QCD, could ever possess such a property of permanent quark confinement. Next slide, please. A breakthrough in this regard was the idea of the dual superconductor. To appreciate this, imagine a magnetic monopole, anti-monopole pair. Magnetic monopoles don't occur in nature, but a Gedanken experiment with monopoles and anti-monopoles is always possible, and immerse them in a superconductor. The superconductor would tend to expel the magnetic flux everywhere, but flux conservation will not allow flux to be expelled everywhere. This is like the Hindi movie situation where Ajit says, "Isko liquid oxygen में डाल दो, liquid इसको जीना नहीं देगा, और oxygen इसको मरना नहीं देगा," right? So here, superconductivity and flux conservations would lead to this situation. So what's the resolution? The resolution is, in a superconducting ground state, a very thin flux tube would be developed between the monopole and the monopole, and flux conservation would lead to constant energy per unit length. So if the more you want to separate the monopole, anti-monopole, more energy linearly rising with separation has to be supplied to render them free. In other words, the thin flux tube would confine forever a magnetic monopole, anti-monopole pair. So, at least in principle, it was settled that permanent quark confinement is indeed a possibility, but for that, the ground state of QCD would have to be a dual superconductor. Why dual? Because it is not the magnetic charge that has to be confined, but the color electric charge. So we have to switch electric and magnetic attributes. So the QCD vacuum has to behave like a dual superconductor. We are now only passing the buck. Now the challenge is to show that QCD vacuum indeed does behave like that. Next slide. Analytically, this has been a big challenge. Though wonderful ideas have been put forward, we are far from solving this confinement problem analytically. And there is, in fact, $1 million prize by the Clay Mathematics Institute for anybody that will give such a proof. But mathematicians will never accept our proof, and we physicists should not waste our time trying to win this $1 million prize. But numerical studies of QCD or lattice, that has opened the floodgates literally. Now on the lattice, flux tubes can be investigated by so-called Wilson loops, which is what I've shown on the right-hand side, which is just a square or rather a rectangular loop, or what are called Polyakov loop correlators, as shown on the left. The central object of interest is the static quark anti-quark potential. I'm only dealing with pure gauge theory at the moment. Then the expectation value of the Wilson loop would go as exponential of minus t times the quark potential. Likewise, the Polyakov loop correlator will also have the same. So by studying this for large enough R, you can literally measure the static quark antiquark potential, and from there see whether there is indeed a confining force or potential between them. Next slide, please. So for large separations, we can simply expand the potential. The leading term is linear, then the subleading powers like 1 over r, 1 over r squared, 1 over r cubed. Sigma equal to 0 signals linear confinement. You must remember, confinement doesn't require the potential to grow linearly. As long as it grows as any positive power of r, it will be confining. But when it grows linearly, it will lead to linear confinement. On rather general grounds, which I cannot go into, called the open string, closed string duality, you can show, or Lucier and Weiss showed, that the coefficient B is exactly 0. A has the value d minus 2 over 24 pi, irrespective of the gauge group. It's completely universal, depends only on the dimension of space-time, and it is called the Lucier term. It should not be confused with the Coulomb potential, even though it goes as 1 over r, because the realm of validity for this is large distances, unlike the Coulomb potential, which dominates at short distance. The first term is so big that it's very clumsy to study V of r itself, as the first term will dominate everything else. So it is better to introduce a convenient dimensionless quantity, which is basically the scaled second derivative of the potential. Then for the above, it will look like A plus BC over R squared. So for very large distances, the value of this C would be the Lucier term, and then one can see whether the subsequent corrections are not. Next slide, please. There is overwhelming lattice evidence for linear confinement, which manifests as the area law for large Wilson loops. But in addition, rather impressively, even the entire profile of the flux tube has been very accurately studied. And here I show a beautiful result due to Gunnar Bali, etc. Here is the flux tube between a quark and antiquark. And at both the quark and antiquark ends, you see a Coulomb-like peak signifying perturbative quantum chromodynamics, where instead of 1 photon, you have 8 self-interacting gluons, and those peaks can be completely captured by analytical perturbative QCD calculations. But in between, you see a beautiful flux tube that has developed between the quark and the antiquark. Next slide, please.
So you have 25 minutes gone. Okay.
How much more time do I have?
Yeah, please take 5 minutes only
Okay.
for question.
Anyway, the slot is 10 to 10:30. Thank you. So a breakthrough in these studies came from an amazing algorithm by Lucier and Weiss called multilevel. With this, the A term could be studied to 15% accuracy, and they unfortunately stopped short of exploring the most critical region. Next slide, please. So in 2004, as part of the 10th plan, as well as the objectives of an alliance called Indian Lattice Gauge, which I lightly call the LGT Gatabandhan, I built a teraflop linear cluster called Kabru. It was in the top 500 supercomputers of the world twice in a row. I was looking for a worthy problem to put Kabru to work. Next slide,
Sorry,
please.
sir. You're right. I am mistaken. You have enough time. Okay. 15 minutes.
No problem.
No problem.
I'm very conscientious about time. Next slide, please. Next slide. Yeah. So I undertook these studies with Pushan Majumdar. Pushan passed away at a very young age in 2020, who at that time had become a world expert on the Lucier-Weiss multilevel and had applied it to a number of interesting and fundamental problems. We decided to do a very thorough study of flux tubes in 3 and 4 dimensions with SU2 and SU3. Utilizing all the design features of Cabru, we could handle much larger lattices and, more importantly, push to larger QQ bar separations, which turned out to be a game changer. Next slide. So here are the numerical studies, results of the numerical studies. On the left side, you have the 3-dimensional SU2, and on the right side, you have 4-dimensional SU3. What you can see is at the short distance end, there is complete agreement with perturbative QCD, both in 3 and 4 dimensions. And at the right-hand side, for very large distances, there is an impressive convergence towards the string-like potential. So in one slide, it achieves the main message of QCD, that it achieves a beautiful interpolation between asymptotic freedom at short distances to confining string-like behavior at large distance. Next slide, please. Now, the exact potential or the ground state energy of bosonic string theories is the so-called Orvis potential, and you can expand it, and our measured values reproduce this very well already when the quark-antiquark separation was 1 Fermi. So what our studies indicated was that to a high degree, flux tubes actually behave like the fundamental bosonic strings. But bosonic strings are consistent only in 26 dimensions, but QCD is a consistent theory in 3 and 4 dimensions. So how could I use a formula meant for 26 dimensions and formally plug D equal to 3 and 4 and still see the spectacular agreement? A numerological accident? Extremely unlikely. Next slide. So here, Polchinski and Strominger came up with an idea. They were motivated by Polyakov, who showed how to formulate string theory even in 3 and 4 dimensions. But as fundamental string theories, they had a large number of problems. So Polchinski-Strominger idea was to take the message from Polyakov theory that when you go to subcritical dimensions, you have to introduce new degrees of freedom, and therefore they took the string theory action and added to it a non-polynomial term of that type. Next slide, please. Such string theories become consistent in all dimensions. This is a technical point which you have to look at the literature. But the action itself is sick for many configurations, but remains sensible for small fluctuations about a straight confining string configuration. So the interpretation is use the Polchinski-Strominger action as an effective theory. It's also a higher time derivative theory, but it has exactly the same local invariances as string theories. Next slide, please. So we obtained various results, which Peter Matlock analytically showed in 2006, that to order r to the minus 3, the spectrum of these theories is the same as that of bosonic string theories, so vindicating our numerical studies. With Peter Matlock, I also developed a covariant calculus with which effective string theories can be constructed to arbitrary order. With Peter and my ex-student Yashas, we proved a number of results which are beyond the scope of this talk. Next slide, please. So I will end by giving you an effective bibliography. And this is my recent book, String to String, which covers all these topics, all the technical details, vast bibliography, and the theoretical requirements like non-perturbative quantum field theories, dispersion theory, S-matrix theory, birth of string theory, all in one book. By the way, I'm not hinting that you buy my book. The salient results are also summarized in this archive article, Effective String Theories of Yang-Mills Flux Tubes, and that is the archive reference. Thank you very much. And thanks once again for this opportunity, and I'll be happy to answer any questions that may arise.
So thank you, sir. We have about 8 minutes, so we can have a lot of discussion, please.
Should I unshare the file? Can I stop sharing, or should we keep it up?
Can I ask a question to Professor Haridas?
Yes, please.
Tell me.
Hello.
Yeah.
Haridas,
Yeah.
you mentioned about you're familiar with his work on strangeness, right? He showed that I think it's deuteron, where he found that you need strangeness to understand the spin of the levels. Is that correct?
No, this dual string model I've not really studied very much, so I'm afraid I can't answer your question.
I see. Do you know anybody else here, Professor Mitra, who might? I'm curious. No, I've forgotten this.
What exactly is the question? Maybe I can rephrase it in a different way.
You want me to rephrase the question?
You can ask your question. I'll see if I can rephrase it in my language.
Okay. Professor A.N. Mitra had discovered the presence of strangeness by studying the nuclear energy levels. If I remember right, it was deuteron or triton. I don't know whether it is H2 or H3. Do any one of you remember the argument?
Okay. No, not me.
All right. I will look up and I think I'll be able to find out.
Sure. I will also do that.
Okay, good.
Might I ask a question, please?
Yeah.
Sir, can you little bit more elaborate about the effective string theory? What is the effective means here?
I didn't hear you very well. Perhaps you could type your question on the chat and I can read it. I'm a bit hard of hearing in spite
I'm
of
asking
my
about
hearing aid.
I'm asking about the meaning of effective string theory.
The meaning of the effective string theory.
Sorry?
The meaning of the effective string theory.
Yeah.
That is the question.
What about the effective string theory?
Meaning, yes.
Yes.
Exactly.
It's exactly like effective field theories. For example, long before QCD was solved, we had an effective chiral field theory of pion and pion-nucleon interactions. The spirit is exactly the same. In superconductivity, the Ginzburg-Landau effective theory was successful in explaining many things long before the BCS theory came about. So effective string theories will capture the symmetry aspects of strings, but not very detailed requirements like the action be well behaved, etc., etc. So they will be valid in a limited domain of string configurations, but not for all string configurations as a fundamental string theory would do.
Okay, thank you, sir.
Professor Nimai, may I ask a question, please?
Please continue, please.
So, Professor Haridas, I was just curious. This Polchinski-Schrodinger's action that you showed, is it ghost-free?
Yeah. Well, no, it is both closed. I mean, the one I wrote was for closed strings, but there is an open string version of the Polchinski-Schrodinger's action also. So, in fact, there is a notion of an open closed string duality even for these effective string theories. So closed strings is not a restriction.
Now, what I'm asking is it ghost free?
Both string.
Ghost, because it has higher order time derivative terms?
No, of course not. Because, you know, it is goes free in certain domains, in the sense that the effective strings also do not excite any negative norm states. But if you go to very short distances and apply this theory, you will have all the sicknesses of string theories, bosonic string theories.
Right, thanks.
Any more question, please? So otherwise, I was told that Professor Mitra also had some work before the event, before color hypothesis, that we need some sort of extra degrees of freedom. He used to call nodes and anti-node. From his calculation, he saw that there is a need for extra degrees of freedom in old quark model. Later on, it was called color. So I heard like this, but I don't know much in detail because it was not my work.
Well, I have also heard this, but
Mm.
I have used color in a very precise sense,
Yes.
as used by Gelman, Fritsch on one side, and Hahn and Nambu on the other. And I am not aware of any work of Mitra which identified color in such a,
Yes,
you
right.
know, deeper level, but I could be mistaken.
So if there is no further question, let us thank Professor N.D. Haridas for his extremely useful talk. Thank you, sir. Thank you.